Hello, Physics 1. Welcome back to part 2 of Monday's lecture. Sorry for that really quick cutoff. Okay, so we had just talked about looking at the moment of inertia for a bike wheel. So that would be a wheel where all of the mass is focused on the outside rim, and we're neglecting any mass relating to the axle and the spokes. By the way, if this is something that you're really interested in proving again, I'll just repeat that very rigorous calculations can be conducted in a classical mechanics class, and that's where the proof of these assumptions lie. They're just a little bit beyond what we can do in a Physics 1 class. So we talked about how the moment of inertia, which is how much it's going to resist rotation, is equal to the mass times the radius squared. All right, so let's do a practical example. All right, so we have a bike wheel or a bike-like wheel within a bike-like wheel. So we've got an axle in the middle. So the smaller wheel weighs 7 kilograms and has a radius of 11 centimeters. The larger wheel out here weighs 3 kilograms and has a radius of 28 centimeters. Now it's got some forces on it. So we've got the force of gravity pulling directly down, and then you also have the normal force of the axle. And now let's say that you had a string wrapped around it, and you're using that to rotate the wheel in place. So here's the string, and it's experiencing a tension force from your hand. And we're going to say that this has a nearly frictionless axle. Okay, so here is the setup that we're going to be analyzing. Now we're pulling the string of negligible mass to make it spin. It's going to get faster and faster and faster, increasing the rotational speed of the wheel. So the rotation changes from 3 revolutions per second to 8 revolutions per second. What we want to look at is how much work did you do? So what that's cluing us in right there is you are not going to be in the system. You're going to be outside of the system so that you can do work on it. Also, just one thing to note, this is not radians per second. Keep that in mind. Okay, so we know that the final energy is equal to the initial energy plus any work done. So therefore, there isn't any translational kinetic energy. The rest mass is staying the same. So the only type of energy that we're dealing with is rotational. So K rotational final is equal to K rotational initial plus any work done. So given from where the problem started, going from 3 to 8, it started already in motion. Okay, so we know how to calculate rotational kinetic energy for a bike wheel-like object. So we have 1/2 I omega squared final is equal to 1/2 I omega squared initial plus work. Work is equal to 1/2 times the moment of inertia, omega final squared minus omega initial squared. Okay, we need to deal with I. So we know the generic formulation, but we don't have exactly a traditional wheel. But what we actually have by looking at a bike wheel, what we have just derived is I for a ring. And this is essentially a ring situation. Bike wheels are rings. And so we've got a ring and then we have another ring inside, and we know that I ring is equal to mr squared. Okay, we also know that we've got two objects here, so the moment of inertia is going to be equal to the moment of inertia of the inner wheel plus the moment of inertia of the outer wheel. So this is how you handle a situation like this. You look to see how can you break this into parts where you already know how to calculate it. Remember, in physics, you're going to get problems that you know everything already in how to do. The trick is to basically figure out what you already know. Okay, so now that we know where we're going, so we have I being equal to I inner plus I outer is equal to mi r squared I plus mo r squared O, and we have the values for that. So the inner wheel is 7 kilograms, 11 centimeters in radius, therefore that's 0.11 meters squared, plus 3 kilograms times 0.28 meters quantity squared. Our moment of inertia for this system is equal to 0.32 kilogram meters squared. And yes, that is the correct units for a moment of inertia. Okay, so now we need to handle something else. We need to convert revolutions per second to radians per second. And this is straightforward. So omega initial is equal to 3 revolutions per second. We can do this by saying there's 2 pi radians in 1 revolution. So this is equal to 18.8 radians per second. And for omega final, we just do the same thing. We know there's 8 revolutions per second times 2 pi radians per 1 revolution is equal to 50.3 radians per second. All right, so before we go after the work of the hand, let's deal with the other forces. So have we accounted for all the work? So we know that things doing work, or things doing forces. We have the hand, the earth, and the axle. Now the hand is definitely doing work. So we know that we are pulling it over a distance, applying a tension force. So that's very straightforward. Okay, so yes, work. Now let's talk about the earth. Okay, so it's staying in place. Is there a delta y? Well, it's equal to 0. So no work. What about the axle? And remember, we said at the beginning, it's frictionless, or good enough for government work. Also no work. Okay, so the work is only coming from the hand. All right, it's all you, baby. So let's see. Work is equal to 1/2 0.32 kilogram meter squared times 50.3 squared minus 18.8 quantity squared. That would be kilogram meters squared, kilogram meters squared. And so work is equal to 348 joules. Okay, so we did that by recognizing that work was basically the leftover between the initial and final rotational kinetic energy, which was the only type of energy that we were dealing with in the situation. Then the differences could be accounted for by the work being done. All right, so, and then one thing to note if you used momentum principle. So momentum principle has to do with translational kinetic, or with a translational movement. If you were to add up all of these forces, and then F string, added together, they will equal 0. Because while it is spinning, it is not moving over a distance. Okay, so, and the MVCM is not changing. Okay. So next up, we have how to calculate the moment of inertia in theory. So basically what I'm going to step you through is how these calculations are made, so that when I just present you with different equations for different types of systems, you know how they were derived. So deriving them is a little bit beyond this class. Those of you in the calculus class could certainly do a simple derivation for this, but they get somewhat complicated and they really are beyond the scope. So I'm going to skim through. But I do believe it is important for you all to know where something comes from. And many of you throughout the semester have asked, where does something come from? So sometimes we have an explanation that is appropriate for this level of class, and sometimes it's a little bit beyond. This one is a little bit beyond, but still something that I can give to you. Of course, if you really want to do this, classical mechanics, we don't offer it here. You can take it at Dort. You'll do it over and over and over and over again for increasingly complex systems. It is fun and tedious all at the same time. Okay, so what we're going to do is we're going to walk through this. For a rod spinning on axis. And it's perpendicular. So basically what I mean, here's a rod, we'll say it's very, very thin, and it's spinning around, so like this. Okay, it has length L, mass M, and thickness small compared to length, and it has uniform density. Okay, so this is the situation that we are dealing with. Okay. So, given what I've just said about it, we can say every centimeter has the same mass. And this is because rho is constant throughout. So step one, to go after the moment of inertia, which remember is a sum after all, is you're going to divide this into slices of n numbers. So we're just going to cut it up into pieces. So we'll take our rod. Here it is. And then we've got an equal number of slices on each side. We're going to put the origin at the point of rotation. So each one of these is delta x. And so we've got L over 2 here and minus L over 2 over here. Okay, so delta x is equal to L over n. And the mass of one slice is equal to delta m is equal to m divided by n the number of slices. I should have written a capital N here. Okay. So now we're just setting it up to do this sum. And we want to add up all the slices to get I. Okay, so let's start with one slice. We're going to look at slice located at x sub n 0, 0. Delta m is equal to m over n, and delta x is equal to L over n. And n, therefore, is equal to L over delta x. Therefore, delta m is equal to m over n is equal to m over L over delta x is equal to m delta x over L. So all we've done is just a little bit of rearranging. Okay, now that we have an expression for the mass of each slice in terms of the total mass, the size of the slice, and the total length, then we need to find out how much each slice is contributing to the moment of inertia. Okay, so we need delta I of a slice. And we're going to assume all the atoms of a slice are the same, are perpendicular away. So they're all the same distance from the center. So basically, you've got a slice. You're just going to assume, okay, all the atoms are, we're just going to pretend they're here. Okay. So, or actually, it's more typical to do that they're all off to one side. Actually, you'll see either approach. Delta I is equal to delta m x squared sub n, which is equal to m delta x over L x squared n is equal to m over L x squared n delta x. So all we've done here is we're just building the moment of inertia formula for this particular one. Okay, so now we need to add up all of our i's. We add them up. So I is equal to the sum from little n equals 1 to n. Delta I is equal to m over L x squared n delta x. So we're just pulling out the constants in front of our summation. I is equal to m over L. Now we want to take the limit as these slices get smaller and smaller and smaller. So n goes to infinity. N equals 1 to n, xn squared delta x is equal to, of course, the integral from x initial to x final, x squared dx. So I is equal to m over L. We're going to integrate from minus L over 2 to plus L over 2. X squared dx is equal to 1/12 ml squared. And this is how a moment of inertia is calculated for different systems. So this integration step of figuring out how you would divide it into slices, how you could standardize the distance from the center of mass, and to get the moments of inertia contributions for each individual slice, so then you can integrate over them to get a moment of inertia. So that's where the expressions I'm about to give you, how they are derived. So you don't have to do these derivations, but I don't want to just present you a formula, if I can ever avoid it, without giving you some explanation of the deeper understanding of where it's coming from. They don't come out of thin air. And yes, these have been measured and verified. Okay, and if you think this is a fun process, again, I will repeat, classical mechanics. This is where you do this. Okay, so now that we know where a bunch of moments of inertia come from, so you just learned the moment of inertia of a rod. So I rod is equal to 1/12 ml squared. And this is, of course, it must be rotating on its axis there. So these are for very specific situations. Okay, so let's do a few more moments of inertia. So we have a cylinder. And the axis of rotation is down the middle, and it's rotating this way. So it's rotating like that. It has length L, radius R, mass M, and the moment of inertia for the cylinder is equal to 1/12 ml squared plus 1/4 mr squared. And you can see that that moment of the inertia for the rod is embedded in there, because essentially what you have is a rod with enough thickness that you must account for it in its moment of inertia. Okay, so now let's say we had a disk. And in this case, it's rotating like this. Now, let's say you had a disk and it's rotating in the middle, so like this. And it will have some radius R, some mass M, rotating in the middle. And so this is essentially, you could do this for a disk. You could also do this for a cylinder rotating with an axis of rotation cutting down through the center here instead of bisecting it. So I disk is equal to I cylinder is equal to 1/2 mr squared. Okay, and now you could have a sphere so rotating right down the middle. I sphere is equal to 2/5 mr squared. So this would be a sphere rotating like so. All right, so those I just expect you to know. They were all derived using the method that I showed you before, and I do allow you on quizzes to bring the moments of inertia with you just because it's a lot to memorize. And memorizing them is not that important. Okay, so, but just know that those are things I do expect you to know, but I do give you an out. So, rigid rotation about a point not the center of mass. So everything that I've just showed you there has been so far stuff that's rotating around the center of mass. So let's say you had, here's this, and it's rotating around like that. So this is clearly not rotating around the center of mass. So this is much heavier than that. So we have some RCM. So this is not So let's talk about how we go after kinetic energy. So we can start from the general expression. Kinetic energy total is equal to K translational plus K relative. K relative, in this case, is equal to K rotational. So we have a ball, a rod. So the angular speed of the ball will equal the angular speed of the rod. So K rotational will be equal to 1/2 ICM omega squared. And the question is, what about K translational? Because the center of mass is moving. So the center of mass rotates about the axle with angular speed at distance RCM from axle. So we can go ahead and write that in. There we go. So speed of the center of mass in meters per second is VCM is equal to omega RCM. So K translational is equal to 1/2 mv squared cm is equal to 1/2 m omega r cm quantity squared. K translational, just to repeat, 1/2 mr squared cm omega squared. K total is equal to 1/2 mr squared cm plus ICM omega squared. So that's why we rewrote that, is so that we could get it into this pretty format here. And we can basically summarize this by saying that K total is equal to 1/2 I omega squared, where I is equal to m v squared cm plus I cm. So you could call this whole thing the moment of inertia. And what we have just shown here, this is called the parallel axis theorem. So K total is equal to K translational plus K rotational is equal to 1/2 mv squared cm plus ICM omega squared. And this requires rigid, that's an R, rigid body with rotation rate being the same. Okay. So, moving on. we have a thin rod with mass 230 grams and 80 centimeters long, with omega being equal to 26 radians per second, and it's rotating at 30 centimeters from one end. Okay, so let me draw a picture. Here's our rod. It's 80 centimeters long. This is the center. It's rotating from here. Now, this is 10 centimeters from the center. Yeah? And we know that it has omega of 26 radians per second. So it's basically like I'm taking this pen and rotating it here, off center. Okay, so K rotational is clearly not zero, and K translational is also not zero. The center of mass is moving. So and RCM, so the point from which it is moving, is 10 centimeters, or 0.1 meters. So K total is equal to K translational plus K rotational is equal to 1/2 m r squared cm plus ICM omega squared. K total is equal to 1/2 mr squared cm plus, we're dealing with a rod, so that's going to be 1/12 ml squared omega squared is equal to 1/2, we'll factor out that m, r squared cm plus 1/12 L squared omega squared. New page. K total is equal to 1/2 0.230 kilograms times 0.1 meters squared plus 1/12 0.8 meters squared times 26 radians per second, quantity squared. K total is equal to 4.92 joules. All right, so that is how you do rotational kinetic energy. So I think this is a good place to stop, and I'll see you for Tuesday's lecture.